Hello students, we have done an example of simple modeling using exponential function in class before, and now we are going to use that to try and model our population data. You have entered the data on GeoGebra, and this is more or less how it looks like when you plot the points. And similarly to our example before, we are going to try and make a model in the form of y equals a times p power x. And we are going to choose 2 points to find the values of a and b in this function. So the first point we will use is 0,472, which is the first point in your data. And by doing so, then you can substitute the values to the equation. And since a number power 0 is 1, then from here we get that our a value is 472. So knowing this, we will write our new function now, 472 times p power x, and we still have to find the value of p. So we are going to pick 1 point in the data to substitute into this function, and I'm going to choose 50,825.81. And think about it, you might want to choose another point and just give a reason or explanation why you think that point that you have chosen is the best one. So if I use this point, then I will substitute into my function and we'll get something like this. And applying balance method, we can divide both sides by 472, and afterwards we can take the 50th root of both sides, and using your calculator, then up to 3 decimal points, then you will get the value of p, which is 1.011. Now let's try and see what happens. So we have now a function that looks like y equals 472 times 1.011 power x. And if I go now to GeoGebra and try to enter these values to graph and try to see how the graph looks like and whether it actually fits your data. So I'm going to type here y equals 472 times 1.011 power x. And if I press enter, so here is where you type your function, and then if I press enter, then the graph looks approximately like this, and you might think that, oh, this might not be the best fit of the population data. So maybe you then now think, oh, okay, shall we try and do a bit of a transformation, applying what you have learned so far? So let's say we are going to introduce some other things. So a here, if we have as a starting point p power x, which is an exponential function, adding this a multiplication by a, then you know that there is a vertical stretch. If I put, let's say, a c here, c times x, so another number introduced to the function, then this is going to be a horizontal stretch, as you know. And maybe I'm still going to do something else, which is a vertical translation. So let's try first with this and see how technology, in this case GeoGebra, can help us. So I'm going to just make this graph disappears, And all right, we are going to try and use a slider now, or a couple of sliders actually. So as you remember, we are going to have 1, 2, 3, 4 parameters here, and I'm going to make a slider for each of them. So here is my first slider, slider A. And our previous function that we have developed algebraically has a value of a of 472. So if I would like to try a couple of other values, I might think, oh, okay, start from, let's say, 300 and to maximum of 550 with increment of, let's say, 10 or something. So every time you slide it, then you will it will increase, or it will move or change by 10 units. So let's try that. The second slider I'm going to use is a b, so which is the base of our exponential function. In this case, I'm going to use a value of 0.85 to, let's say, 1.5. Think about it. Think of a reason why we use these values. I'm going to keep this increment the same, 0.1. For C, for parameter C, I'm going to use 0.125 with same increment. And for D, let's say, remember this was our vertical translation, so let's say going down 100 to going up 100 or something with increment of, let's say, 10. So let's see what happens. So now I'm going to type this function here into my function input. So I will type y equals a times b to the power of, don't forget to put bracket here, cx, and then still plus d. So if I do so with the values that this slider shows here now, so 300 for a, b is 1, and so on and so on, then it looks like a straight line. However, if I just change something a little bit, so for instance here in b, if I change it a little bit, then the graph looks completely different already. So if I keep at 1.05, let's say, and now try and change C. Oh, wait a minute, something is not right here. I have not put the CX, so that's what we're still going to do. Right. Now, so then now if I change the value of C, then we are going to see some change in the graph. So you see here something is going on, and then I can still move my graph up and down using the slider for D. So try this. Try to make your own sliders. Start from your own function. Look at how your function that you have developed algebraically looks like, and think of the sliders and the values that you want to use, and try to find the best fit, the best graph for your data values.